In this video, I will finally be able to show you how to graph a polynomial function by putting all of those things that we've talked about together. Things we know. The graph of a polynomial function is a smooth, continuous graph with no holes or gaps. So in other words, you should be able to draw this graph without picking up your pencil. The degree and leading coefficient determine the end behavior of the graph. We will want to find the zeros of a polynomial function by factoring if possible. And just remember that a polynomial function has at most n zeros, where n is the degree of the function. We use the multiplicity of zeros to determine if the graph will cross the x-axis or bounce off the x-axis at an x-intercept. The graph of a polynomial function of degree n has at most n minus 1 turning points. And just to kind of reiterate that fact, a linear function, right, a line, the graph is a line, has degree 1, and there are 0 turning points in that. A quadratic function has degree 2, and there's 1 turning point at the vertex. So just making sure that you connect what we're learning now with the things that you've already seen before. We have an example now where we want to graph the polynomial, and my goal for you, of course, you could turn on your calculator and get the graph, but I want you to be able to sketch the graph by hand. And with all of the facts that we've learned, I'll show you that that's not such a horrible process. And through this, we want to identify the zeros, the y-intercept, the end behavior, domain, and range. I haven't asked specifically for you to find the relative extrema in this problem, but you could certainly use your calculator in conjunction with what you do by hand to find those points. So we first start by identifying the end behavior. Let's get that out of the way, and then we'll go through some of the other steps. So we know that this is an odd degree, right? The degree is 3. And we have a positive leading coefficient, which that positive leading coefficient is a 1. So just from that information, remember the basic graph of y equals x cubed is down to the left and up to the right. So there we already know how it's going to look at the ends. Now we want to find the zeros. To find the zeros, we set the function equal to 0. That's x cubed plus 3x squared minus 9x minus 27 equals 0. So we have 4 terms which we will use grouping to factor. The first 2 have an x squared in common, so that leaves x plus 3. The last 2 terms have a negative 9 in common, and dividing that out leaves x plus 3. And that's equal to 0. Now we have a common binomial of x plus 3 that we will factor out. So we have x plus 3 times the remaining factor of x squared minus 9 equals 0. The x squared minus 9 is a difference of squares that factors as x plus 3 times x minus 3. So notice that we have a factor x plus 3 that repeats twice. So that 0 will have a multiplicity of 2. So we get x plus 3 equals 0, or x minus 3 equals 0. One of our zeros is 3. The other is negative 3. So negative 3 has a multiplicity of 2. 3 has a multiplicity of 1. So we know a lot about the graph already. We know that it's going to cross or touch at -3 and 3. Specifically, we know at -3 it will bounce off, and at 3 it's going to cross through. We also know even more because we know the end behavior. So if it starts down to the left, what we know is that it's got to start down from the left and go up to this x-intercept, but it bounces off there, so it's going to have to come back down. So we'll find out a little bit more about that. And then also at the 3, it's going to cross and then go on up because it's in behavior as it rises to the right. So there's some things that happen in between there, and we also know it's not ever going to cross the x-axis again, so it's going to go down and come back up. Well, where will it go down? Let's find the y-intercept. The y-intercept is found by replacing x with 0, that is finding p of 0. If we plug in 0 in place of x, we're going to get 0 cubed plus 3 times 0 squared plus 9 times 0 minus 27, which is just -27. So we know the graph crosses the y-axis at -27. Now what you could do is find more points. If you want some more detail in this graph, I could find an ordered pair on the graph between my intercepts. So I could choose to plug in a value between -3 and 0, and then between 0 and 3 to get more points. I showed more points in the table in Top Hat. So for instance, one of the points that I found in Top Hat was -1, -16, and I also found the point 1, -32. I found several more, but honestly, knowing those points is enough for us to get a rough sketch of the graph, because that tells us that it's going to bounce off like we know at -3, come down through the y-intercept and then go down a little bit further, and then it's going to come back up. So that would be the rough sketch of the graph. The domain and range for an odd degree function, recall that is just all real numbers. Now, if I wanted to graph this on my graphing calculator, I would just caution you that you'll need to adjust your window so that you can see all of those turning points. Because we see by hand that the y-intercept is -27, you need to make sure that your y values go down to be able to see that point. So you might want to set your y min at -40 and your y max at 40, just so that you can see an appropriate viewing window to see all of those key points of the graph. Example B is p of x equals -3x times x plus 2 times x minus 5 times x minus 1. Notice that the degree of this polynomial is 4, right? Because if you remember, we can look at only the leading term of each of those factors. They're all linear factors, so it's sufficient then to multiply each of those leading terms to get what the leading term of the entire polynomial is, which is -3x to the 4th. So this has an even degree, and we see that it has a negative leading coefficient. Remember that an even degree and negative leading coefficient means that it will go down to the left and down to the right. Now we can find the zeros of the function. And recall we set the function then equal to 0, so -3x times x plus 2 times x minus 5 times x minus 1 equals 0. Fortunately, this is already factored, so it is sufficient to just set each of those factors equal to 0 to solve for those zeros. Doing that gives us x equals 0, right? We divide negative 3x equals 0, divide that equation by negative 3 to get x equals 0. X plus 2 equals 0 gives us x equals negative 2. X minus 5 equals 0 gives us x equals 5. And x minus 1 equals 0 gives us x equals 1. Notice that each of these have a multiplicity of 1 because the factor that represents that 0 has an exponent of 1. Graphically, that tells us that the graph will cross the x-axis at each of those zeros. I'll place those on the graph. We will plot 0, 0, negative 2, 0, 5, 0, and 1, 0. Another key point we can find is our y-intercept. So the y-intercept is found by evaluating the function at an input of 0. We would get negative 3 times 0 plus 2 times 0 minus 5 times 0 minus 1. But 0 times anything will just be 0. So the origin is our y-intercept. Now the other thing that we know is that it has an end behavior of down to the left and down to the right. The graph is going to be down to the left of negative 2, and it's going to have to cross the x-axis at negative 2, so it's going to go up to some point, and then it's going to have to come back down to go through 0, 0, and then it's going to go down, and then it's going to have to come back up to go through 0, 1, and then it's going to have to go up again and then come back down because we know to the right of 5 it is down again. So to figure out what that high point needs to be, again, you can use your graphing calculator to help you, and you can evaluate the function at a few values. So if you want to evaluate the function between negative 2 and 0, 0 and 1, 1 and 5, and I did that in the top hat table. If I plug in negative 1, the function is 36. At 2, the function is 72. And at 4, the function is 216. Now these are a scale of 50. So at 2, I'm going to go up to 72. And then at 4, it's 216. So we can fill in our graph to know that it's going to go up to those points. Now the 4, 216 may not be the exact highest point, but then it's going to have to come back down pretty steeply to get to that 5, 0, and then the graph will go on down. Again, you can do this more precisely with the graphing calculator, but it's going to be important for you to get that initial feel of what the graph is going to look like, because we're going to get into inequalities in a few sections where knowing where the graph is above or below the x-axis is going to be really important for that. And so if you can have the concept down just by looking and really knowing the end behavior, knowing the behavior at the zeros will kind of tell you if it's got to be above or below the x-axis in those intervals. So again, just try to keep thinking about the information and how it all ties together. And then I want to show you one last example. Let's say that f of x equals negative x cubed plus 5x squared minus 6x. We know the end behavior already because this is an odd degree, right? The degree is 3. and it has a negative leading coefficient, namely -1. So the end behavior tells us it's going to be up to the left and down to the right. If we find our zeros, we're going to let -x cubed plus 5x squared minus 6x equals 0. We will solve this by factoring. There's a common factor of a -x. Dividing by -x leaves x squared minus 5x plus 6 equals 0. Factoring x squared minus 5x plus 6, we need to find the factors of 6, whose sum is -5, and that will be a -3 and a -2. So the factored form is -x times x minus 3 times x minus 2 equals 0. Setting each of these factors equal to 0, we have -x equals 0, which gives us just x equals 0. X minus 3 equals 0 gives us the solution of x equals 3, or x minus 2 equals 0 gives the solution of x equals 2. So the zeros are at 0, 0, 3, 0, and 2, 0. Notice that each of these have a multiplicity of 1. So the graph will cross the x-axis at each of those points. The y-intercept, if we plug in 0, find f of 0, we're just going to get 0, right? Replacing each of these x's with 0 leaves nothing but 0. Now, we know our end behavior is up to the left, so that means to the left of 0, it's going to come from an upward direction. And we know it has to cross the x-axis at that 0, so it's got to go down to some point, and then it's going to have to come back up to go through the 2, 0, and then it's going to have to come back down to go through 3, 0, and then it stays down. So the basic shape is like this. The domain and range is all real numbers. That just reminds me, I forgot to do the domain and range of the previous problem. The domain is all real numbers. The range, we would actually need to find out what the relative extrema is so that we know what the maximum point is. And once we know that maximum point, then we could figure out what the range is. So it would be -infinity to whatever that max value is. So I'll leave that to you to find that relative max on your calculator, and the y value of that point would have to be here for the range. Now if we wanted to get a more precise graph, just keep in mind that I can plug in values. Like if I wanted to plug in a 1, I could get a -1 plus 5 times 1, so -1 plus 5 is 4. Minus 6 would be a -2. So if I wanted to be a little bit more precise here, I would know the graph is going to be at 1, -2. And then maybe at 2.5 I'd have to plug in a value if I want to see how far it goes up above the 2, between the 2 and the 3. I'd have to use my calculator to obtain that value. And when you plug in the 2.5, you actually get a 0.625. So the graph really has just a very slight rise between the 2 and the 3. And then if you wanted to find values to the left of 0 and to the right of the 3, you could. But again, the point of this right now is just to get a sketch of the graph. The calculator can certainly give you more precision on that.